Hello classmates, today we will learn about the operation and maintenance of voltage transformers in the context of outgoing feeder bay equipment. In this lesson, we need to understand the function and working principle of voltage transformers, as well as knowledge about their operation and maintenance. This will enable us to analyze and handle faults in voltage transformers. At the same time, we will further develop awareness of electrical safety and analytical skills, fostering good professional qualities. The key and difficult point of this lesson is the operation and maintenance of voltage transformers. So if a voltage transformer fails in actual production, how should we maintain it? This requires a thorough familiarity with the basic principles and functions of voltage transformers. A voltage transformer is essentially a special type of transformer consisting of windings and a core. It is very similar to a transformer. Both are used to change the voltage on a line. However, the purpose of a transformer changing voltage is to transmit electrical energy. Hence, it has a large capacity, usually measured in kilovolt amperes, kV or megavolt amperes. The purpose of a voltage transformer changing voltage is primarily to supply power to measuring instruments and relay protection devices. It is used to measure line voltage, power and energy, or to protect valuable equipment, motors, and transformers in the line when a fault occurs. Therefore, the capacity of a voltage transformer is very small, usually only a few voltamperes or tens of voltamperes, with the largest not exceeding 1000 voltamperes. The standard rated secondary voltage of the secondary winding after transformation by a voltage transformer is 100 volts. Its electrical symbols are represented in the following two ways, as shown in the figure. The first is a two-winding voltage transformer, and the second is a three-winding voltage transformer. Its characteristics are: first, the primary winding has many turns and is connected in parallel to the primary circuit of the power supply system. Second, the secondary winding has very few turns and is connected in parallel to measuring instruments or relay protection devices. Third, the secondary side load impedance is large, so changes in the secondary load have a negligible impact on the primary side. Fourth, under normal operating conditions, the secondary winding is close to a no-load state. Therefore, the following points need to be noted when using voltage transformers. First, the secondary side of a voltage transformer must not be short-circuited. This is mainly because the internal impedance of a voltage transformer is very small. If a short circuit occurs, it will generate a very large short-circuit current, which could burn out the voltage transformer. Therefore, forces must be installed on both the primary and secondary sides of the voltage transformer for short-circuit protection. Second, one end of the secondary side of the voltage transformer must be grounded. This is to prevent high voltage from the primary side from entering the secondary side if the insulation between the primary and secondary windings breaks down, thereby endangering personal and equipment safety. Here, it needs to be emphasized that students must develop good electrical safety awareness when using electrical equipment. Third, the wiring of the voltage transformer must be correct. The primary winding should be connected in parallel to the circuit being measured. The secondary winding should be connected in parallel to the voltage coils of the measuring instruments, relay protection devices, or automatic devices. At the same time, attention must be paid to the correctness of the polarity. Voltage transformers are allowed to have certain errors such as ratio error and phase angle error. The influencing factors are primary voltage, secondary load, and power factor. Therefore, based on the accuracy class of voltage transformers, they are divided into 5 classes: 0.2, 0.5, 1, 3, and 5 among them. Voltage transformers with class 5 accuracy are generally used for measurement, while those with class 0.2 accuracy are used for precision instrument measurement. There are many types of voltage transformers. According to the working principle, they can be divided into electromagnetic voltage transformers and capacitive voltage transformers. Among them, the principle of electromagnetic voltage transformers is suitable for power systems of 6 to 110 kV. They are expensive, have large capacity, and compared to the latter, have smaller errors. Capacitive voltage transformers are suitable for systems from 110 kV to 500 kV. They are low in price, small in capacity, and compared to electromagnetic voltage transformers, have relatively larger errors. According to the number of phases, they can be divided into single-phase voltage transformers and three-phase voltage transformers. Single-phase voltage transformers measure single-phase voltage. Single-phase types can be made for any voltage level. Three-phase voltage transformers measure single-phase line voltage and are generally only used for voltage levels below 20 kV. In addition, voltage transformers can be divided into indoor and outdoor types based on the installation location. Generally, those for 35 kV and below are mostly made as indoor types. At the same time, based on the windings, they can be divided into three-winding voltage transformers and two-winding voltage transformers. Three-winding voltage transformers have two secondary windings. One is the basic secondary winding for measuring instruments and relays, and the other is an auxiliary winding, namely the open delta winding or residual voltage winding, used to reflect single-phase grounding faults or zero-sequence voltage. According to the insulation medium, they can be divided into dry-type, oil-immersed, cast resin, and gas-insulated types. Among them, dry-type voltage transformers are only suitable for indoor distribution installations at 6 kV and below in dry environments. Cast resin voltage transformers are made by casting the primary and secondary windings together with the leads into a hole using epoxy resin. They are used in indoor distribution installations for 3 to 35 kV. SF6 gas-insulated voltage transformers are generally used in power systems of 110 kV and above. How should voltage transformers be installed in terms of wiring methods? Let's learn about this in detail below. Figure shows the wiring using one single-phase voltage transformer. The left figure is mainly used in grids with non-directly grounded neutral points at 35 kV and below to measure line voltage. The right figure is mainly used in grids with directly grounded neutral points at 110 kV and above to measure phase-to-ground voltage. In Figure B, two single-phase voltage transformers are used, or in Figure C, one three-phase voltage transformer is used. Both can form a VV connection, also known as an open delta connection. It is mainly used in grids of 20 kV and below with ungrounded neutral or neutral grounded via an arc suppression coil. It is used to measure three-line voltages but cannot measure phase voltage or be used for insulation monitoring. Figure D uses three single-phase three-winding or one three-phase five-limb three-winding voltage transformer connected in Y0Y0 with an open delta connection. The secondary winding connected in Y0 measures the phase voltage of the grid and can be used for insulation monitoring. The auxiliary secondary winding connected in open delta provides zero-sequence voltage. Figure E shows a Y0Y0 connection composed of three single-phase voltage transformers. It is used to measure three-phase voltage and can also be used for insulation monitoring. After everyone has understood the basic knowledge and wiring methods of voltage transformers, let's now learn about their operation and maintenance in actual production. The inspection items for voltage transformers mainly include the following. First, check whether the porcelain bushing is clean, free from defects, cracks, and discharge phenomena, and whether the sound is normal. Third, check whether each connection point is overheated or sparking, whether the bolts are loose, and whether there is any abnormal odor. Fourth, check whether the secondary circuit is open, whether the ground wire is in good condition, and whether there is looseness or breakage. Fifth, check whether the three-phase indications of the voltmeter are within the allowable range and whether the voltage transformer is operating under overload. Classmates, during the operational inspection of voltage transformers, if any of the following faults are found, they should be immediately taken out of service. First, the porcelain bushing is cracked, and severe discharge occurs. Second, the high-voltage fuse blows twice in a row. Third, the shell temperature exceeds the allowed temperature rise and continues to rise. Fourth, oil leakage is severe, and the oil level cannot be seen in the oil gauge. Fifth, the high-voltage winding insulation breaks down, accompanied by smoke and a burning smell. Sixth, there are internal discharge sounds, other noises, or spark discharge phenomena. Everyone should combine the course content and carefully verify any suspicious problems found during work. It is essential to ensure meticulousness and rigor during the inspection process to guarantee the safe operation of power plants and substations. Classmates, in this lesson, we mainly learned about the function and working principle of voltage transformers, as well as their operation and maintenance. We learned that voltage transformers convert a larger primary voltage into a smaller secondary voltage through a certain ratio for metering. They are also crucial for the precise measurement, control, and protection of the power grid. This requires students to have a deep understanding of the principles, structure, and wiring methods. For example, Zhu Mengmeng, the head of an innovation studio in Yunnan Power Grid, discovered problems such as difficulty in capturing abnormal data, checking circuits, and locating faults during his work. He successfully developed an operation and inspection instrument for AC and DC electronic transformers. He also invented a method for assessing the metering error state of capacitive voltage transformers, saving the company over 10 million yuan. So, please also combine this example and integrate innovative thinking and an attitude of identifying problems into the process of solving problems. Complete the following after-class assignments. That's all for the content of this lesson. Thank you, everyone. Goodbye.